and I'm taking a top-level view from this talk, and I'm going to sort of go through a couple examples and talk about, what are the characteristics that may or may not make something detectable when we're talking about, is it on? I'm not supposed to use that one because it makes a lot of feedback. I have a lavalier mic. Can people hear me? Does that work better? Okay, I'll try to shout. So the detectability of biosignatures across interstellar distances. Maybe that doesn't actually work. Okay. In the middle. Okay, perfect. Okay, so the top level question we're trying to answer is, how do we actually determine if an exoplanet is inhabited? We've talked this week a lot about biosignatures. We've talked this week a lot about false positive biosignatures. Let's now talk about what we can actually see across interstellar distances. Okay, so, this is what we want to see. We want to see other Earth-like exoplanets, and by Earth-like, I really do mean planets that are, similar to Earth in that they are habitable and inhabited. But of course, as we've discussed during this week, we're not necessarily, we're not at all going to get spatially resolved information from exoplanets. We're just going to get pale blue and other colored dots. And from these dots, we have a lot of questions we want to answer. The perhaps most profound question that we want to answer is, do these dots have life? And that's a big question to ask of a pale blue dot. But we know how to do it. I mean, we've been thinking about how to do this for quite some time. So let's consider now what actually makes a good biosignature across interstellar distances. So let's actually go back to the basics, and let's think about what we've learned from our solar system. Our solar system has a wide diversity of worlds, planets, and moons in it. And from these planets and moons, we've learned a lot about what we can and cannot remotely sense from across interplanetary distances. We heard earlier this week about Jupiter's moon Europa and Saturn's moon Enceladus. And the reason why we're so interested, and we've also talked a little bit this week about Mars, the planet next door. And of course, we're going to also talk about Earth and, some, examples of biosignatures that may or may not be detectable from our own planet. Okay, so let's start with these icy moons. So we've heard earlier this week about how these icy moons may be habitable. They may have habitable environments in their subsurfaces. So under these icy shells, you might actually have oceans of liquid water. We have little smiling microbes that might actually be able to sustain themselves, especially if there's a water-rock interface at the bottom of the ocean. You can drive chemical gradients that microbes could exploit for metabolism. So that's great and that's exciting, and we've spent a ton of time studying these worlds. We have orbiters, we have had orbiters around both Jupiter and Saturn, and we've studied them remotely from observations from Earth, and we've stared at them quite a lot, trying to understand what exactly might the subsurface conditions of these worlds be like. And yet, despite the vast amount of time that we spent scrutinizing these worlds, we don't actually have any idea of whether they actually have life in their subsurfaces. So I know it sounds trite, right? Like it's obvious, or at least it should be, but subsurface life is not something that you can remotely observe, or at least it's going to be extremely hard to remotely observe it. Maybe you could see something if they're spewing out plumes of geysers with bacteria in them, or maybe the cracks on Europa have some sort of upwelling from the subsurface. This has been suggested in the past, but this is really hard to do. And the reason why I bring up this point is the fact that oftentimes when we talk about the habitable zone, people point out, correctly, that the habitable zone is not, the be-all, end-all of habitable environments in our solar system. There are these icy moons that also have potentially habitable environments in their subsurfaces. However, the habitable zone was designed as a practical construct for exoplanets, and it tells us where we can actually look on exoplanets and see, actually detectable and remotely detectable signs of habitability and life. You can't remotely detect these signs of habitability on these moons from across interstellar distances. We can barely do it across interplanetary distances from our solar system, right? So the habitable zone concept is for exoplanets. These worlds are still habitable though, right? So the habitable zone is not all the habitable environments in the universe, but it does tell us where we can actually search for habitable conditions on exoplanets and search for signs of life on exoplanets. Okay, so now let's turn to Mars. And I hesitated a little bit putting this section in because I know this is a little bit controversial, but I'm going to talk about methane on Mars. There have been purported discoveries of methane on Mars that I'm sure everyone is familiar with. And this is very exciting to a lot of people because of the fact that, as you've been hearing throughout the week, the dominant source of methane, at least for Earth, is biology. And so when people hear about this idea of methane on Mars, our minds go, ooh, you know, could there be life there? There's this possibility, this tantalizing possibility. The story is, it's complicated. So this paper was published by Mike Mumma in 2009, where he published this report of ground-based observations of seasonally and spatially variable methane on Mars at the tens of parts per billion level. So here, as a function of latitude on the y-axis and the methane mixing ratio on the x-axis, for those who don't study atmospheres, the mixing ratio simply means the fraction of the atmosphere that's composed of a given gas. So that's the methane fraction of the atmosphere in units of parts per billion as a function of seasons. So the different colored contours are different seasons. And, you know, like, oh my God, people were like, there's methane on Mars. What does this mean? And it's seasonally and temporally variable. But there's complications. So one of the complications is the fact that they were staring through Earth's atmosphere to make these observations. And as Kevin Donnelly has pointed out, unless you very, very carefully and accurately remove that telluric Earth's atmospheric signal from your observations of this, you know, very, very faint trace gas on Mars, they argue rather convincingly that telluric contamination may be responsible for these, you know, ground-based detections of methane on Mars. The drama continued when the Curiosity rover in situ on Mars reported, you know, variable amounts of methane, suggesting they're seeing seasonal variability of methane on Mars. So you can sort of draw this sinusoid curve through these points for these different Mars years, denoted by these different colors. And they were like, well, lo and behold, like we went to the surface of Mars and we measured methane. So clearly there's methane on Mars. Very, very exciting. But then the drama continued because then the ExoMars Trace Gas Orbiter, which is in orbit around Mars and was, you know, designed to be sensitive enough to see methane from orbit. If you're getting these plumes from the surface, they should be spread out over, you know, over the planet to some sort of global background level. And the Trace Gas Orbiter should have been sensitive enough to see those, to see that methane, but it didn't see anything, right? So there was a null detection here. So what's going on? And then to continue the drama, just last month, June 2009, I don't know why I said 2006, 2016, June 2019, there was a 21 part per billion detection reported by the Curiosity rover on the ground, which is literally off this chart if you look at the y-axis. Okay, so what is going on? Well, your answers will vary depending on who you talk to, and I'm not going to give you my opinion because I don't want to get involved in this debate. But depending on who you talk to, the answers will vary dramatically. And if you talk to a skeptic about methane on Mars, they would say, well, you know, the Curiosity, you know, the methane that was detected by Curiosity, it could just be outgassing from the rover. Like maybe it's something we brought to Mars, and that's why the ExoMars Trace Gas Orbiter didn't see anything. So despite the fact that Mars is, you know, cosmically, it's not just next door to us, it's like in our house, it's so close to us compared to the exoplanets. And despite the fact that we have literally gone there in situ, we still don't know with any degree of certainty, although, you know, I guess that sort of just does depend on who you talk to, but there's still a lot of uncertainty in the community of what exactly is going on with this question of methane on Mars. So I think this teaches us a number of things. So gases that are present in these tiny quantities are going to be potentially quite challenging to detect in exoplanet atmospheres. You don't necessarily want to look for these tiny signals that take a lot of effort to pull out of your data. And also, just a corollary to this point that I want to bring up is that when you're staring through Earth's atmosphere to see the same gases that we have in the atmosphere of an exoplanet, you might have a really bad time unless you're extremely careful of correcting Earth's atmosphere and correcting that telluric contamination. Okay, so moving from Mars now to Earth. I'm going to spend a number of slides talking through some of just, a small fraction of Earth's potential biosignatures and what I think about them. So this photograph, this beautiful photograph, is a picture from the Blue Ridge Mountains.
Hi. Good morning.
Good morning. How are you?
Good. How are you?
Very good.
What can I get for you?
Thank you.
Anything else?
Aliens. So the Blue Ridge Mountains are between Virginia and Tennessee, and they're called the Blue Ridge Mountains because they have this really lovely blue haze that hangs low over these mountains. Very, very beautiful. So I want to talk through, using this image, some of the potential biosignatures that one might or might not be able to detect on an exoplanet. One of the loveliest papers, scientific papers that I've read, and if you know me, you know that I really love hazes, so it might not surprise you that I love this paper. It's called Blue Hazes in the Atmosphere. And in this paper, Dr. F.W. Wentz describes this phenomenon of these blue hazes that occur in certain places on Earth, like the Blue Ridge Mountains, like the Blue Mountains in Australia, various locations where you have heavily vegetated landscapes. And what he goes through in this paper, various, potential explanations for how you might form these hazes. Maybe there's some sort of atmospheric water vapor or smoke, or some sort of abiotic atmospheric particles. But he ends up concluding that these hazes are actually probably a byproduct of a class of compounds called terpenes, which are emitted by trees and various kinds of vegetation on our planet. So these hazes are themselves a type of biosignature because they are themselves produced by life. And this class of compounds, these terpenes that are producing these hazes, are a very wide class of compounds. They're found in a number of things, a number of organic things. They produce beautiful scents that we smell. They're very volatile compounds. They give trees their smell. They give flowers their smell. They're in various kinds of alcohols. They're all over the place, and they're emitted in large quantities into our atmosphere. So people have suggested, could these terpenes, like for example, could isoprene, which is the simplest terpene, the smallest unit of terpenes, be a biosignature? These terpenes are emitted into the atmosphere at about the same total, I think it's emitted at like 500 teragrams per year, I think, into the atmosphere, which is similar to the amount of methane that's emitted into our atmosphere per year. Right? So we often talk about methane as a biosignature, but how come we aren't talking about isoprene, for example, as a biosignature when it's getting emitted into the atmosphere at roughly the same rate as methane? So people like Sarah Seeger and other authors have, suggested that perhaps this is this could be an interesting biosignature to think about. These terpenes that form these hazes. The tricky thing with these terpenes is they don't survive very long in the atmosphere. Isoprene survives on the order of a couple hours in our planet's atmosphere, compared to methane, which survives on the order of about 10 years in modern Earth's atmosphere. So these gases, they don't last long. They get destroyed really rapidly. And that means that they're present in really tiny quantities. So the amount of methane in our atmosphere is on the order of about a part per million. These terpenes are in the atmosphere on the order of like parts per billion, right? So they're really, really tiny trace compounds. They're hard to detect because they have such a low abundance, despite the fact that they're being emitted into our atmosphere, quite rapidly. Okay, so, maybe they would be challenging to detect. And then, well, I love hazes, so, well, could these blue hazes, separate from these terpenes themselves, could these blue hazes be a sort of secondary biosignature that points to the existence of these organic compounds? And as far as I know, nobody has actually studied this in detail, which is too bad because hazes are awesome. I suspect that it would be extremely difficult to detect these hazes in a global average because they're only present on a very small fraction of our planet. And I also suspect that it might be difficult to distinguish the blue scattering slope from these hazes from the regular Rayleigh scattering that occurs from our planet's atmosphere. Now, they might produce other absorption features at other wavelengths. I don't know that this has been well studied, though. So I suspect that blue hazes, at least for a planet like Earth, would be a challenging type of biosignature. So do I think terpenes and blue hazes are a viable biosignature for exoplanets? Well, you probably think my answer is no, but my answer is actually that you have to think about these biosignatures in the context of their environments. For an Earth twin around a solar twin, I think that these would be extremely challenging biosignatures to go after, but it hasn't, as far as I know, this hasn't been studied in other photochemical contexts, right? So a case in point, I think Vicki talked about this in her talk earlier this week, is, and I know Stephanie also brought this up during her talk, is this case of methane and Earth-like atmospheres around other stars, right? So when you have gases being emitted into the atmosphere in different photochemical contexts, they can accumulate to different levels. So here is a figure. Oh, I think the credit is being cut off. So this is from a paper by Antigona Segura from 2005, I believe. So altitude on the y-axis, the methane mixing ratio, again, that's a fraction of the atmosphere composed of methane. On the x-axis, this is the exact same planets with the exact same source boundary conditions at the surface of methane being put around the sun versus being put around these two different M dwarfs. And the different photochemical conditions under these M dwarfs is leading to orders of magnitude more methane in that particular photochemical context, right? So context is always really important. So are these terpenes and blue hazes a viable biosignature for exoplanets? Well, I don't know, because they haven't been studied in these different contexts, as far as I'm aware of. So we have to think about them in their proper context in order to evaluate any given, novel or unusual biosignature in the right context. But until we do that, we have to be really careful about, what we do think or, is or isn't a good biosignature. And this is really always true, right? This isn't just for terpenes and hazes. This is for every single biosignature. Okay, so now let's go back to this photograph, and let's think about what's probably the most obvious remotely observable sign of life, which is these trees that you see, these beautiful trees. Okay, so we've heard earlier this week about the reflectivity of plant life, and you've heard about this feature called the vegetation red edge, I believe. So the vegetation red edge is where plants, these plants become extremely reflective at infrared wavelengths. So longward of about, roughly 0.75 microns, plant life is extremely reflective. So here is a tree in visible light. And here's that same tree in infrared light, right? So it's extremely bright. If you compare the brightness of the tree and the brightness of the grass, compared to the sky and clouds and visible light compared to infrared light, you can see, wow, this is extremely bright in infrared light. It is extremely reflective. People have looked for this vegetation red edge in disk averaged or disk integrated views of Earth, for example, using Earthshine observations. And they find that you can see it. So here is some Earthshine observations from one of Maggie Turnbull's papers that I found. And I'm highlighting here the vegetation red edge with that green box. So you can see it in disk integrated spectra. It's present at about the 2 to 10% level in planetary spectra. So it might be a sort of challenging feature to go after. It's not the strongest feature in the world, but it is there, right? It's proof of concept, right? It is right there. You can see it. And there are other kinds of pigments that also produce their own reflectance signatures. So here's a really pretty set of photographs in a paper by Eddie Schwieterman highlighting, in particular, different kinds of colorful microorganisms. For example, these sort of pink fuchsia organisms down here in panel C. So those are halophiles. This is actually the salt ponds near San Francisco. If you ever landed at San Francisco Airport, you might have actually seen these as you're landing. I've seen them myself. They're really, really beautiful from the air. They are, in fact, extremely vivid colors. It's pretty spectacular to see. And so, it's not necessarily to suggest, right, that, plant life on an alien exoplanet is going to have exactly this spectral signature. But this is just a proof of concept, right? And there's other kinds of pigments that we know exist on Earth and that one might be able to detect in a disk average spectra, right? So here's some various Earth spectra covered by various different types of organisms. You can see that they produce dramatically different, spectral shapes. Again, this is from a paper by Eddie Schwieterman. So, is the red edge a viable biosignature? I would rephrase this more generally. Are surface reflected biosignatures a viable biosignature? Well, for Earth, at least, from our disk averaged Earth, we can see the red edge. So I think that's a good proof of concept that yes, it may be possible to detect these surface reflectance biosignatures in a global average view. We do have to be careful though about considering abiotic mimics for these biosignatures. There are, of course, so many mineral compounds that produce their own reflectance signatures, and we're going to have to be very, very careful about ruling those out when trying to determine whether a potential surface reflectance biosignature that we see on an exoplanet is truly biotic versus abiotic. So this picture that I picked, by the way, is because it's from infrared light, and right, so the horses are super dark and the trees are super bright here. So they are the obvious biosignature. They're easier to see in this image. So I think probably, and I think it actually may be harder to do this, distinguish surface reflectance biosignatures from abiotic mimics, than it might be to actually detect them themselves. They will both be challenging, I think, but I think really convincing ourselves that we're truly seeing something that's not explainable through some combination of abiotic materials might be a little bit hard, but it may be possible. Like we shouldn't necessarily rule it out. Okay, and then the last potential biosignature that I'd like to discuss from this image is, the most invisible one, but probably the most obvious one, which is the oxygen that's in the air above these trees and these mountains. And we've heard throughout the entire week a ton about oxygen. We've talked about the history of oxygen in our atmosphere. We talked about, why oxygen may be a good biosignature. We talked about oxygen false positives, blah, 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 right? So oxygen has been in our atmosphere for a long time. It's been produced on our planet for billions of years, going all the way back to sometime in the Archean, when we think oxygenic photosynthesis evolved, but it took until roughly 2.5 billion years ago during the Great Oxidation Event for oxygen to start to build up to detectable quantities in our planetary atmosphere. We've talked about false positives for oxygen. Because oxygen is such an important biosignature for Earth, we spent a huge amount of time thinking about the ways that planets can fool us by producing false positives. Oxygen that's not actually produced by biological processes, but produced from these abiotic processes. So is oxygen a viable biosignature? Well, I'm not going to belabor this point because we've been talking about oxygen all week. Yes, of course, I think oxygen is a good biosignature. It produces strong global features. This isn't a gas that's, concentrated on, certain pockets of our planet's atmosphere. It's all over the planet at a large amount in our atmosphere. And it produces, we think, distinguishable false positives. So we think, at least as far as our studies have taken us so far, that we're able to distinguish abiotic oxygen from true biological oxygen that's produced from various kinds of photochemical processes, as we heard about yesterday. So considering, again, the worlds of our solar system, what are the top level characteristics of a good biosignature that you need to think about when thinking about is a given characteristic of produced by life a good biosignature? Well, you have to think about the reliability of that biosignature. Can you distinguish it from false positives? Or is it going to be extremely difficult to distinguish it from false positives, right? Life can produce, life can release nitrogen into the atmosphere as part of the nitrogen cycle. But nitrogen is a huge abiotic background gas in our atmosphere. Life can emit CO2 into the atmosphere, but CO2 is emitted in vast quantities by volcanism. So how would you distinguish the two? Maybe seasonal variability, as Stephanie was saying, but we have to think about these things. So reliability of a biosignature, and can you distinguish true positives from false positives, is very, very important. A survivability of biosignatures, do they actually last long enough in an atmosphere to, raise to a level that you can actually detect it? Terpenes are an interesting example of this. Methane on Mars is an interesting example of this. If methane is actually being produced on Mars, it is being destroyed extremely rapidly in the troposphere, much more rapidly than our models can readily explain. And that's perhaps why the trace gas orbiter hasn't seen it. Maybe it's just getting destroyed absurdly rapidly in the lowest layers. Terpenes are destroyed extremely rapidly in our Earth's atmosphere. So can something actually survive? Just because something is produced by life doesn't mean it's going to build up to large quantities in the atmosphere. And lastly, of course, and the title of my talk, right, is the detectability of biosignatures across interstellar distances, you have to explicitly think about detectability. Does something actually produce spectral signatures that you could see with instrumentation that you anticipate having? So these three properties make what we would consider good biosignatures. You can look at Vicky Mehta's paper about oxygen as a biosignature, where she discusses oxygen in the context of each of these three characteristics. The biosignatures that we talk about for Earth-like planets most frequently, like methane, oxygen and ozone, and vegetation, the reason why we talk about those, these sets of biosignatures is because they fill all of those characteristics, right? They're detectable, they're reliable in the sense that we think we could distinguish them from abiotic mimics, and they're survivable. They last long enough, at least in an Earth-like context, that we have a chance of detecting them. And so we haven't just picked this set of biosignatures because these are our favorite gases for whatever reason. We've picked them because they still fill this set of criteria. And as we expand our thinking about biosignatures to other kinds of more novel biosignatures, we still have to consider these three factors. What's ultimately detectable, when we think about novel biosignatures, might not always be intuitive, and it's always context dependent. So, for example, Sean Goldman did a study where he was thinking about organic sulfur gases, which are produced by life on Earth. They're not a large byproduct of life on Earth, but they are produced by certain classes of microbes. So here's a type of microbe. So I'm not going to try to pronounce that name. Here's a type of microbe that produces a type of organic sulfur gas called methyl mercaptan, or CH3SH. You might imagine there could be exoplanets out there that produce lots more organic sulfur gases than our own biosphere produces. So perhaps there's exoplanets out there where you have, lots and lots of organic sulfur gases entering the atmosphere. What happens when that happens? Well, gases like methyl mercaptan are readily photolyzed. And when they're photolyzed, they're broken up into CH3, the methyl radical, and SH. And those methyl radicals love to react with each other, and they form ethane. And what's interesting and what was surprising was that the methyl mercaptan gas, the organic sulfur gases in general, were not easily detectable in the spectrum. They were actually quite hard to detect. What was readily detectable was this excess of ethane that you build up to higher quantities than you would anticipate through methane-only photochemistry. So normally ethane in a planetary atmosphere is a byproduct of methane. So if you were to look at an exoplanet and measure the amount of methane and see, oh, well, it's got way too much ethane for the amount of methane that it has, you might be able to infer the presence of other kinds of gases that are introducing these methyl radicals into the atmosphere. So maybe you could, indirectly back out that there must be some other, there must be some other gas there. Maybe it's life. So here, the non-intuitive conclusion was that instead of the biosignature being these organic sulfur gases, the actually detectable biosignature was this excess of ethane. And the only way to figure that out was to actually run a full-up photochemical model where you study this in the context of the rest of its environment. I also looked at these organic sulfur gases in a photochemical model, and I found that when you pump them up to even higher quantities and put more methane into the atmosphere, you can actually, they can actually start to contribute to organic haze particle formation. So organic hazes are similar to the hazes that are in the atmosphere of Saturn's moon Titan. So these are those orange hazes that cloak Saturn's moon Titan. And we think that earlier Earth's atmosphere during the Archean may have had periods when it actually was covered with these organic hazes, during particularly methane-rich periods. Now, for a planet that had a lot of organic sulfur gases being produced, you can actually start to form these haze particles as one of the byproducts. So here's another unexpected result, right? These organic sulfur gases could actually start to form these hazes at lower methane concentrations than you might predict if you didn't have the organic sulfur gases in play in the atmosphere, right? So non-intuitive, you actually have to run a photochemical model to figure this out. So ideally, I think when we start to think about these novel biosignatures and these, these different kinds of biosignatures than we've traditionally studied, we can't just, say, okay, life emits this gas, therefore this gas is a biosignature, and we're done. We can't do that. What we ideally would do is we think about, okay, what does life produce? And then, think about, okay, well, these are potential novel biosignature gases. And then, unfortunately, like this isn't the Hitchhiker's Guide to the Galaxy. We can't build test planets where we put these gases into an atmosphere and run that experiment in real life. But we can do the next best thing is we can run computer models where we, inject these potential biosignatures into an atmosphere with different stellar spectra, and then we can see what actually happens. And from that, maybe some of these are novel detectable biosignatures that one could actually see in a planetary spectrum, or maybe they produce secondary products that could themselves be detected. And for the good candidates, then that could feed into future telescope design. So if we find something we think is really interesting and we would like to go after, we have to think about, okay, well, what kinds of wavelength range, what kind of spectral resolution, what kind of signal to noise do you actually need if you're actually trying to observe this? And so these are the kinds of things that we have to think about when designing potential future space telescopes like HABEX and LUVOIR that will be designed to search for signs of life on exoplanets. Okay, so again, we have to think about detectability, survivability, the reliability of all biosignature gases. Other considerations that we always have to keep in mind are interstellar distances demand that we look for global signatures. If we're in California, if you're flying over a California poppy field and it's filled with orange flowers and you're looking for the one flower that's that's purple in color, it's going to be really hard to find that one purple flower, but the orange flowers, which are your global signature, are going to be easy to spot. So just because life produces something, if it's only produced in a tiny corner of the planet and it doesn't cover the planet globally, it might be very hard to detect. The planetary and stellar context matters. Just because life is producing something, in the Earth context doesn't mean it's going to produce that same something as a detectable biosignature in other contexts, or vice versa. Right? Methane in an oxygen-rich atmosphere for modern Earth doesn't build up to super large quantities in our atmosphere, but it can build up to much larger quantities around an M dwarf. So thinking about this context is always absolutely critical. Our detection method matters. I didn't spend a huge amount of time talking about this, but depending on how you're viewing the planets, like, for example, if you're viewing oxygen in an exoplanet through Earth's atmosphere, it might be quite difficult to convince yourself that you're actually seeing oxygen in the exoplanet's atmosphere and not oxygen in our own planet's atmosphere. And lastly, you have to rule out false positives in all cases. When you think about biosignatures, as we've been discussing during this week, we always have to be extremely careful that we're not going to fool ourselves. Okay, and that's it, and I'm happy to take questions. Hey, questions for Giada?
Yeah, hi, what is the actual loss process for the terpenes? Is it photolysis, or do they just fall out or make bigger particles, it's sediment, or why do they go away?
The terpenes are, this is where I need to do my own research. I believe they are attacked by OH radicals in the atmosphere. I believe that is the loss process. It might also be photolysis involved. I would have to look back at the papers, but they are removed extremely rapidly from our planetary atmosphere. So you might imagine, there could be contexts of planetary environments that are not removed as readily. Yeah, photochemistry. Oh, it's too early in the morning. Oh, my favorite question. So I've thought a lot about organic hazes, the type of organic hazes that form in the atmosphere of Saturn's moon Titan. And these are strong red UV absorbers, right? So Titan is orange because these hazes absorb all the blue light. So they don't have a spectrum to show you, but they produce these spectra that are extremely red. So if you're seeing something where all this blue light is getting absorbed, if you're seeing something with the shape of Titan spectrum, that is an extremely good indication that you're seeing hazes. The hazes produce absorption features themselves at longer wavelengths. So the type of organic haze in Titan's atmosphere produces absorption features at about 3 microns and about 6 microns. So you might be able to look for those absorption features Accessing those wavelengths might be challenging to do with direct imaging, but you might be able to do it with transit observations. The 6-micron feature is stronger, quite a bit stronger than the 3-micron feature. So, you know, you could potentially go after it with JWST. They also produce in transit strong scattering slopes, where the light is getting much more strongly scattered at shorter wavelengths compared to longer wavelengths, where they're much more transparent. So hazes are great from a detectability standpoint because when you have a global haze, like for example for Titan or potentially for our keen Earth during very methane-rich periods, it dramatically changes the shape of our spectrum, like in a huge way. It'd be hard to miss the haze. You have to be really oblivious if you miss the haze, because the haze is super obvious. These blue hazes haven't been studied in nearly as much detail at all, but they obviously produce very strong scattering slopes in the blue. That might be hard to distinguish from Rayleigh scattering, but I don't know what other absorption features they might produce at longer wavelengths.
On the topic of hazes, like in some of the recent observations, like people have been, like the spectrums that people have observed also fits really well to like a flat line. And then people just say that it could be hazes.
Yeah.
So in those cases, they are not seeing any strong like feature that will tell you that, oh, this is actually a haze. So what do you think about that? Yeah.
So that's why a lot of exoplanet observers hate hazes, because there can be various types of aerosols more generally, like clouds and hazes together, that can obscure deeper atmospheric features, especially in transit. So transits sense long path lengths through the atmosphere because you're looking in long tangent paths through the atmosphere. It's like looking at Earth during sunset when the sunlight is passing tangentially through the Earth's atmosphere and all that blue light's getting scattered out because it's passing through so much path length. So hazes and clouds are particularly difficult to deal with in transit. In direct imaging, it's not quite so bad because your path length is much shorter. So a haze that's transparent in direct imaging can become opaque in transit because you're going through so much more atmosphere. And this is what people are seeing when they look at some of these hot exoplanets and they find no signs of gaseous absorption features because these various types of aerosols in their atmospheres are totally obscuring the absorption features they might be looking for. For a planet like a Titan analog or an early Earth analog, organic hazes that are similar to what's in Titan's atmosphere are not quite so bad to deal with. They become quite a bit more transparent in the near infrared. So longward about 1 micron, they're much more transparent compared to in the visible region. So again, they produce these scattering slopes, so you can still see absorption features from gases despite that. And in direct imaging, when you're looking through a shorter path length, you can still see strong absorption features across the whole wavelength range, basically. Ty, who's talking next, he's published a paper where he actually looked at the transmission spectrum of Titan, and proof of concept, like lo and behold, there's this scattering slope from the haze, but there's also methane features imprinted above that haze. So they're not so terrible. They're not necessarily so terrible.
I was just wondering about the reflectance biosignatures about the pigments. Do you know if there are some studies that try to understand what could have happened with pigments in the past Earth, like in the Archean Earth, what those pigments how they could have been spread on Earth?
Nikki, if she was here, would be a better person to answer this question. I know that people certainly have thought about the evolution of pigments on our planet, and I know that certain kinds of pigments, I believe they can leave chemical remnant fossils in the fossil record that we could actually try to infer when different types of pigments evolved on our planet. I don't know too much about it beyond that. Certainly, the shape of the spectrum hitting Earth's surface was pretty much the same, not, not exactly the same, but almost exactly the same in the Archean as compared to today. So if there were hazy periods, you would be getting redder photons, so it might be a little more akin to what you'd receive at the surface of an M dwarfish type of planet. But the hazes in Earth's atmosphere only existed, we think, for relatively transient periods. So I don't know if that would be long enough to actually drive the evolution of different colors of pigments. Yeah.